Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. So we move on to the second last chapter, which is hypothesis testing for engineering statistics. So what is a confidence interval? So this is important term that we have to really identify, which is an interval that contains a set of plausible values of the parameter, and it is always associated with the confidence level, which is 1 minus alpha, which measures the probability that the confidence interval actually contains the unknown parameter value. And most commonly used confidence interval for a population mean is the two-sided t-interval. So this is a really important formula, yeah, for you to really take note. Okay, let's take a look what is
Welcome.
confidence interval.
In this video, I'll be constructing confidence intervals for a population mean, assuming the population standard deviation is known. A confidence interval constructed from sample data is a range of values that is likely to include the population parameter at some specified confidence level. The confidence interval for a population mean is determined by taking the sample mean, the point estimate, and subtracting and adding the margin of error to it. So if the population standard deviation is known, the margin of error is determined by Z alpha over 2 times sigma over square root of n, where alpha, the significance level, is 1 minus the confidence level, and correspondingly, the confidence level is 1 minus alpha. So if the confidence level is 95%, alpha will be 1 minus 0.95, which equals 0.05. Z alpha over 2 here is a single value called the critical value. It can be found in the normal tables or by using software. When constructing a 95% confidence interval, for example, the confidence level 0.95 is in the middle of the distribution, and the remaining 0.05 alpha is divided equally into the two tails as 0.025 each. From the less than cumulative standard normal tables, 0.025 in the left tail corresponds to a Z value of negative 1.96, and due to symmetry, it will be positive 1.96 for the right tail. So the Z critical value corresponding to the 95% confidence level, which we write as Z.025, is 1.96. Let's look at an example. Scores on an exam are normally distributed with a population standard deviation of 5.6. A random sample of 40 scores on the exam has a mean of 32. We want to construct confidence interval estimates for the population mean at 80, 90, and 98% confidence levels.
Okay, so this is basically a very standard question that usually be asked during the test, or especially for the final examinations, especially in determining the population mean with the different confidence interval. So let's proceed.
The margin of error is going to be Z alpha over 2 times 5.6 divided by the square root of 40. We now need to find the critical value for each confidence level. For the 80% confidence interval, alpha is 0.2, so we have 0.1 in each tail. Looking up 0.1 in the normal tables, we find the closest value to be 0.1003, and that corresponds to a Z score of negative 1.28 in the lower tail. And because of symmetry, it is 1.28 for the upper tail. So the Z critical value for the 80% confidence level is 1.28. The margin of error is therefore 1.13. So the lower limit of the confidence interval is 32 minus 1.13, which gives 30.87. And the upper limit is 32 plus 1.13, which gives 33.13. To interpret that, we say we are 80% confident that the population mean score is between 30.87 and 33.13.
Okay, please take note, yeah. Hold on.
With 90%.
Okay, please take note. How do I click on this?
Confidence alpha is 0.1. So we have.
Where is the thing?
0.0.
Okay, right now after this, I want you, after you have learned about the 80% confidence, so I want you to do for 90% confidence and 98% confidence, and write down in the comment section down below. Okay. Okay, so and make sure you don't forget to rewind this YouTube, and make sure that you fill in everything accordingly according to the previous data, because those are the important points that usually give mark, because it is a complete set. If you missed it, then you're gonna miss the whole of it. Okay, so I think next one is okay. Okay, p-value, the probability for the null hypothesis to be true, which is a p-value of the measure of the plausibility or credibility of a null hypothesis, which is h null value between 0 and 1, and it observes the level of significance, which is usually it is denoted as h null. This one ho, which is h not h null hypothesis. And the smaller the p-value, the less possible is the null hypothesis, which leads to the leads to the rejection of null hypothesis in favor of alternative hypothesis. So in this next topic, the importance of determining the difference between H null, which is the null hypothesis, and alternative hypothesis, which is HA. So in general, null hypothesis H null is rejected when p-value is smaller than 0.01, and in general, null hypothesis is accepted when p-value is larger than 0.10, and which indicates that the null hypothesis is plausible, although this does mean that it has been proven true, and p-value is in the range of 1% to 10% is generally taken to indicate that the data analysis is inconclusive. Okay, so in this we can take a look at the different and
Hey everyone,
the
so today I will be talking about p-value and what does it represent in statistics. Statistics is everywhere. If you see this touchpad carefully, what you see is a normal bell-shaped curve. Let's say p-value in this region is 0.01. This means I touch over here 1 in 100 times. Let's say the p-value in this region is 0.8. This means 80 out of 100 times I'm going to touch in this region. Now if we see the statistical definition of p-value, then p-value is the probability value for the null hypothesis to be true.
So you can see the relation between the probability that we have learned in the earlier chapter with this hypothetical testing.
To understand p-value, first we should try to understand null hypothesis. The null hypothesis is the hypothesis which treats everything same, everything equal. Let's take an example where plants are treated with fertilizer A and fertilizer B. The null hypothesis here will be there's no difference in the effect of fertilizer A and fertilizer B. Now there are many statistical tests, say for example t-test, f-test, ANOVA, etc. And the final result of each test is judged on the basis of the p-value obtained. The p-value can take any values from 0 to 1. Let's say p-value is 0.1. This means if I repeat an experiment 100 times, 10 out of 100 times the null hypothesis will be true. Let's say p-value is 0.3. This means if I repeat the experiment 100 times, 30 out of 100 times the null hypothesis is going to be true.
And what about if p is 0.75? What does it indicate? Can you drop in the comment section down below?
Let's say p-value is 0.05. This means if I repeat the experiment 100 times, only 5 times the null hypothesis is going to be true. Okay, let's take an example of t-test. The t-test is used for the comparison of mean. Let's consider the previous experiment where the plants were given fertilizer A and fertilizer B. say a graph represents the mean and the standard deviation in the height of the plant. Now the t-test is going to compare the two means. Let's say the p-value for this test is 0.03. This means if I repeat this experiment 100 times, only 3 out of 100, the null hypothesis is going to be true. Now the next question that arises over here is, should we consider this significant or not? Taking a decision based on p-value is completely in the hands of the experimenter or the scientist who is doing the experiment. The researcher decides the level of significance for his experiment. Let's say the level of significance decided by the researcher was 0.05. Then in this case, the researcher have to reject the null hypothesis. And conclude that there is a significant difference between fertilizer A and fertilizer B. Now let's say the level of significance decided by the researcher was 0.01. Then in this case, the researcher have to accept the null hypothesis and conclude that there is no significant difference between fertilizer A and fertilizer B. So to summarize, the researcher first decides the level of significance, then he does the experiment and finds the p-value. If the p-value is more than level of significance, then the null hypothesis is accepted. And if the p-value is less than level of significance, then the null hypothesis is rejected.
So this conclusion is really important, especially if you are doing your project, which is with especially for the level 3 works. So you can decide your null hypothesis first, and then whether it is significant or not according to the p-value. Okay, so in this case, we can see that the hypothesis that treats everything to be same and equal is null hypothesis, whereby there is no difference in the effect of fertilizer A and fertilizer B. And if we go on a two-sided problem, which to consider the following hypothesis testing, which is H null equals to this one alpha, mu equals to mu null versus H alternative hypothesis, which means that the mu is not the same with the mu null, which say that H null hypothesis equals to null hypothesis HA equals to alternative hypothesis. Suppose a data set of n observations is obtained and the discrepancy between the data set and the null hypothesis is measured through a t-statistic with n minus 1 degrees of freedom. So this is the formula for t-test, whereby this is sample mean and this is a null hypothesis and the sample variance and the sample size. So given this data, and then you try to calculate what is the t-statistic of the data, and put in your comment section down below too. Okay, next one is hypothesis testing step. Okay, the first thing first, you have to state the null hypothesis H null and alternative hypothesis versus HA or H1, and you have to choose a level of significance, whether it is determined by this question or you can set by yourself, and you have to find the critical values, and after that you have to find the test statistic, and you can draw your own conclusion based on the standard template given previously. So the t-values when the value is not provided, and when the sample size is less than 30, so we can use the t-values. solution 4.
Welcome to my second video on hypothesis testing. In this example, we're going to perform a one-tailed test with a t distribution. So let's get started. Here in this example, it says the average IQ of the adult population is 100. A researcher believes that the average IQ of adults is lower. A random sample of 5 adults are tested, and the scores are given below. Is there enough evidence to suggest that the average IQ is lower? So although this example is different than my first video I made on hypothesis testing, the steps are going to remain exactly the same. So let's go over all of the steps to perform an hypothesis test. So here I have written for you all of these steps. And step number 1 says to state the null, which is written with h sub 0 or h naught, and the alternative hypothesis. And the alternative hypothesis is written with h sub 1 or h sub a. It doesn't matter which one you use. So we have to state our null and alternative hypothesis. So let's go back to our example, and let's start with our null hypothesis. H naught, we're going to state our null hypothesis. Now, the null hypothesis is what is currently believed to be true, or what is currently accepted. So in this example, it says the average IQ of the adult population is 100. So the currently accepted value for the average IQ of adults is 100. So the average of the population is equal to 100. This is our null hypothesis. And the null hypothesis is always written with an equal sign. So that's just a little tip. You're always going to use an equal sign for the null hypothesis. So now let's state our alternative hypothesis. Our alternative hypothesis is written with h sub 1 or h sub a, it doesn't matter. And the alternative hypothesis is always what is being claimed. In this example, it says a researcher believes, he is claiming that the average IQ of adults is lower. And these two words are really important. Is lower. He's claiming that the average has gone down, it's decreased because it is lower. So our alternative hypothesis is that the average, which is written with this Greek letter mu, the average is lower than 100. It has decreased. So our alternative hypothesis is that the average is less than 100. And anytime that the alternative hypothesis is written with a less than or greater than symbol, this means we're going to perform a one-tailed test. And I'm going to explain what this means in my next step. But anytime you use a greater than or less than symbol in your alternative hypothesis, this means we're going to perform a one-tailed test. So now we are ready to move on to our next step. So if we go back to our hypothesis testing steps, step number 2 says to choose the level of significance, which is written with the Greek letter alpha. Now this is just the area in the tail. So let's go back to our example. We need to choose our level of significance, which is just the area in the tail. So let me draw a picture of the normal curve for you, just so I'll show you what this looks like. So like I said before, the level of significance is just the area in the tails. And the reason why I chose a level of significance of 0.05 is because this just seems to be the most common value used, and this problem didn't give us the level of significance to use, so I just chose the most common value of 0.05. And notice how the only area, or the only tail that I shaded in the area was the bottom tail. This is because we're performing a one-tailed test, and the reason why I chose to use the bottom tail instead of the upper tail was because the researcher is claiming that the average IQ is lower. He's claiming that it's lower, so the only area of interest is below the average.
So if let's say you want to do the solutions, this graph, this figure is really important. Yeah, don't miss it. Usually student will tend to miss it, and it will cost them marks. So please don't do the mistake.
So if you draw the average of the population on the normal curve, it's always in the middle. So here in the middle, we have our average of the population. And the researcher is claiming that this average has lowered, it's decreased. So the only tail of interest is our lower tail. This is a one-tailed test. And once again, our level of significance is 0.05. Number 3. Now, step number 3 says to find the critical values. Now, the critical values are just the z-value or the t-value that separates the tail from the rest of the curve. Now, I mentioned earlier that we're using a t-test or t-distribution for this particular example. So our critical value is going to be a t-value. Now, let me explain to you why we're using a t-test for this particular example. And I wrote the 2 conditions when we need to use a t-value. And condition number 1 says the population standard deviation, which is sigma, is unknown. Condition number 2 says that the sample size is less than 30. So if we go back to our example, let's see if these 2 conditions have been met. It says the average IQ of the adult population is 100, but it never gives us the population standard deviation. The only thing it gives us is the standard deviation of the sample. So the population standard deviation is never given to us. Our second condition, which states that the sample size must be less than 30, has also been met because we have a sample size of 5. So both conditions have been met to use a t-distribution, so that's why I chose to use a t-test for this particular example. So like I said before, we need to find the critical value, which is going to be a t-value, which separates this area in the tail with the rest of the curve. So in order to find this critical value of t, we need to use a t-table. And one thing we need to keep in mind when using our t-table is the area in one of the tails. We know we have an area of 0.05 in one of the tails. So we need to keep that in mind when using our t-table. So if we go to our t-table and we see that in the top row we have the area of one tail. So we know that the area of one tail is equal to 0.05. So we know that we have to use this row with an area of 0.05. And on the left side of the table, we have our degrees of freedom. The degrees of freedom is always 1 less than the sample size. Okay, we have a sample size of 5, so we know that our degrees of freedom is going to be 4. So we're going to the row with t-value of 2.132. So we have a critical value of 2.132. So if we go back to our example, let's take a look at this curve. Notice how our critical value lies below the average. It's below the middle of the curve. So this means that it's going to be a negative number since it's at the low end of the curve. So instead of a positive 2.132, we know that our critical value is going to be a negative 2.132. So why is this critical value so important? It's because it separates this area in the tail with the rest of the curve. And this area of the tail, which is in red, is called our rejection region. And the reason why this rejection region is so important is because in our next step, we're going to perform a test. And we're going to get a t-value in our test. And if this t-value happens to fall in this rejection region, that means we can reject our null hypothesis. Our null hypothesis says that the average is equal to 100. And if in our test, if our t-value lies in the rejection region, we can reject that the average is equal to 100, and we can accept the alternative hypothesis. So this is why this rejection region is so important. And this brings us to our next step, which is we need to perform a test. Step number 4 says to find the test statistic. And the test statistic is just going to be a z-value or a t-value. And like I said before, we're using a t-test or t-distribution, so our test statistic is going to be a t-value. So if we go back to our example, the formula to find the letter t, our test statistic t is equal to the average of the sample minus the average of the population, all divided by the standard deviation of the sample divided by the square root of the sample size n. And notice how the formula for the test statistic t is almost identical if we're using a z-test as well. So let's plug everything into our formula. First, we'll start with x bar, the average of the sample. We know the average of the sample can be found just by adding all 5 of these test scores and then dividing by 5. So if we add all of these test scores and divide by 5, we're going to get an average of 89. So we know that our average for the sample x bar is equal to 89, and this is being subtracted by the average of the population, which is the Greek letter mu, and the average of the population is equal to 100, so we can plug in 100 for our population average. This is all being divided by the standard deviation of the sample, and just to save a little bit of time, I gave this to us already. The standard deviation of the sample is equal to 15.81, so we can plug 15.81 in for our standard deviation, and this is being divided by the square root of the sample size n. We know that our sample size is 5. And if we plug all of this into our calculator, we're going to get a value of negative 1.56. This value of negative 1.56 is our test statistic. So how do we use this value to draw a conclusion to this problem? That's our last step. We need to draw a conclusion to the problem. So if we go back to our curve, this value of negative 1.56, where does it lie on this curve? Well, we know that this critical value is negative 2.132, and we know this average, which is directly in the middle, has a value of 0. So we know negative 1.56 is somewhere between negative 2.132 and 0. So I'm just going to estimate that our test statistic, which is negative 1.56, is somewhere in between the critical value and the middle of the curve. So this is negative 1.56. So notice how this value of negative 1.56 is not in the area of the tail. It's not in the rejection region, which means that we cannot reject the null hypothesis. Our null hypothesis, which says that the average of average IQ is equal to 100, we cannot reject that. We fail to reject the null hypothesis. Or the easy way to put it is we have to accept it. We accept our null hypothesis that the average IQ is equal to 100. So what is this question asking? Is there enough evidence to suggest that the average IQ is lower? No, there is not enough evidence because we accept our null hypothesis that it stays the same. It's still the average IQ is still equal to 100. So I hope this video.
So these are really important solution, yeah? Especially for you to mention that we should accept or we should reject, and whether we should accept or reject the alternative hypothesis. Okay. For problem with assumed known population standard deviation, so we can use z values, and it is when we have to cite a problem which is to consider the following hypothesis testing, whereby H null versus H alternative, which is indicated by this. Suppose a data set of n observations is obtained and the discrepancy between the data set and the null hypothesis is measured through a t-statistic with n minus 1 degrees of freedom. So the formula is like this. So you have to really know how to put it based according to the value that is given. So critical value, what is critical value? We can use the normal curve table to calculate the z-values called critical values that separate the upper 2.5% and lower 2.5% of sample means from the remainder, which was indicated at this point, for example.
This is Stephanie. This is Stephanie from statisticshowto.com. In this video, I'm going to show you a second hypothesis testing example. In the previous video, I did a one-tailed test, and in this video, I'll be showing you an example of a two-tailed test. I've got a question here about blood glucose levels for obese patients. We're given a population mean and a standard deviation, and we're looking at a researcher who thinks a diet high in raw cornstarch will have a positive or perhaps a negative effect on blood glucose levels. A sample of 30 patients who've tried the raw cornstarch diet have a mean glucose level of 140 and test the hypothesis the raw cornstarch had an effect. Well, there's a lot of information there. Let's break it down into small steps. The first thing I want to do is state the null and the alternate hypotheses. If you aren't comfortable with stating the null hypothesis, then you may want to check out my previous video on how to state the null and alternate hypotheses. My null hypothesis, that's H sub 0, is the accepted fact, which is blood glucose levels are 100. Our population mean is 100. So I'll put mean is equal to 100. And the alternate hypothesis is the one we are testing. Well, the researcher thinks the raw cornstarch has an effect. He doesn't know whether it's going to be higher or lower. So basically, our alternate hypothesis is going to be that the mean, mu, is not equal to 100. So it could be greater, it could be smaller, we don't know. All we're interested in finding out is, was there a difference? The next step is we want to state the alpha level. If the alpha level is not mentioned in the question, then just use the standard 0.05, which is 5%. And what that means is if you take a normal distribution curve, our alpha level is the area in one tail. But we have a two-tailed test because the mean is not equal to 100. If we had the mean is, say, greater than 100, then this would be a one-tailed test because it's just going in one direction. Or if the mean was less than 100, that's also one directional. So we have a two-tailed test. These areas add up to 5%. So we've got half in one tail, 2.5%, and half in the other tail, 2.5%. Now what we want to actually do with this alpha level is find a z-score. We want to find this z-score here, because this is our rejection region, and I will cover the rejection region in just a moment. For right now, I want to find this z-score. I'm going to use a right-hand z-table. The right-hand z-table tells us the area from the mean to any z-score. Now, 1/2 of a bell curve is 50%. This little area is 2.5%, which means this area between the mean and this z-score must be 47.5%. I'm going to look this up in the z-table. I'll actually be looking up the decimal, 0.475. So here's my z-table. I want to find 0.475 in the center of the table. And there's 0.475. It's a z-score of 1.9. That's in the row. 1.9. And if I scroll up, 1.96. So my z-score at this boundary is 1.96. And because the curve is symmetrical, that also means this z-score is 1.96, but this side is negative. So we've got negative 1.96. and positive 1.96. And the last step is we want to calculate our test statistic, and we want to find out if that test statistic falls into this rejection region or if it falls into this rejection region. If it does, we can reject the null hypothesis. And how we do that is with a formula. Z equals x bar is the mean, minus mu of 0, that's the population mean, all over the standard deviation divided by the square root of our sample size n. Well, we're given all of this information in the question, so it's basically just plug in and solve. My x bar, my sample mean was given in the question as 140. Minus my population mean, that's 100 divided by the standard deviation. 15 divided by the square root of the sample size, which was given as 30. And if I figure this out on a calculator, I get 14.6. One final step, there's one small thing left to do, and that is we're going to take this value
14.6
and we're going to see if it falls into one of our rejection regions. Well, 14.6 is much larger than 1.96. This is a z-score, and if it was going to go on a normal distribution curve, it would go way over to the right here, which is in this rejection region. It's larger than the z-score. So we can reject the null hypothesis, which means our alternate hypothesis is now in place, that the mean is not equal to 100. That's an example of a two-tailed z-test. Check us out at statisticshowto.com for more videos and articles and everything elementary statistics.
Okay, now you see the difference between a one-tail and two-tail test, and what are the conditions that we can use it.
This is step.
Okay, so how to set up a hypothesis test? In actual practice, the status quo is set up as H null, and if the claim is boastful, the claim is set up as H1. We apply the Missouri rule, which is show me. Remember, H1 has the burden of proof, meaning to say that we have to prove the H1. In problem solving, look for keywords and convert them into symbols. Some keywords include improved, better than, as effective as, different from, has changed. So these are the keywords that you can interpret. For example, larger or more than, it can be inequality symbol, and smaller or less, it can be less than smaller or less. No more than, at least, has increased, is there difference, has not changed, has improved, is better than, is more effective. Okay, so basically these are the normal type of question that will be asked usually for the hypothetical testing. Okay, so the summary is p-value approach tells us to reject the null hypothesis at the alpha equals to 0.05 level if the p-value less than equals to alpha equals to 0.05. As is the test statistic z equals to negative 1.92, which is less than negative 1.645, we reject the null hypothesis. There is sufficient evidence at the alpha 0.05 level to conclude that the rate has been reduced.
What?
Okay, so thank you. So that's all for this chapter, and I hope you understand, and you can understand the difference between the null hypothesis, the alternative hypothesis, and the application of one tail and two tail, and also the most important part is the standard template of answer, which include the full set of it, whether you want to reject it or you want to accept the hypothesis. Okay, so and this one is really important because you can apply in your experimental works. Okay, so all the best, and I hope we can see in the next final chapter. Okay, thank you. Have a nice day.